Hey there, Lexi. This is Nathaniel. Brig texted me the other day saying you could use some help with a math problem, and I figure I owe him a favor or two by now, so I'm going to give a crack at it and see if I can't make things a little more understandable. All right. So, if I recall, this is the problem at hand. Find the cube roots of 8i and answer in a plus bi form. All right. So, like pretty much all math problems, there's some certain terminology we need to understand in order to produce an answer that makes sense, right? And in this case, you have to understand what cube roots are and what this a plus bi form is. So, since you're in a trigonometry class, I'm going to assume you probably know what a cube root is. It's any number multiplied by itself 3 times that produces your desired result. For example, if I asked you what the cube root of 64 is, you would tell me, oh, it's 4. Because 4 times 4 times 4 is 64. Like that. Magic. And so we are essentially doing the exact same thing in this complex number business. Now, your first reaction to this problem, and mine as well, is sort of, what does complex numbers really have to do with trigonometry? You know, I thought we were dealing with triangles here. What's the deal? And so we will get into that in a moment. A plus bi form is the next piece of terminology. And if you dealt with complex numbers really at all, you're probably mostly operating in this style where you have a real number plus a number with I as the coefficient. That's right. So this is the real portion here, and then this is the imaginary side of the expression. There's other ways to express complex numbers, but this is by far the way you're going to be dealing with it the most. We actually will be getting into a different one called trigonometric form later in the problem. But this is the style they want you to answer in, and that's going to be the status quo for complex numbers in general. All right, so in order to solve this problem, we're going to be using a formula that was created by this guy named Abraham de Moivre, and he was sort of a mathematical genius. He was friends with Isaac Newton and whatnot, and he's most notably known for being the guy that developed a connection between the golden ratio to Fibonacci numbers. That's sort of his claim to fame, but he also created this wonderful formula that we are going to use, and it goes a little something like this. Z equals r to the 1 over n times the cosine of theta plus 2k pi over n plus I sine theta plus 2k pi over n. All right. This is one derivation of it. There's actually quite a few versions of this formula, and this is what's actually known as the nth root formula. Anyway, so let's get into it. I'm going to start by explaining the different variables that we have at play here. First of all, we have the variable z. Z is going to be our answer. It's going to be a root for our expression, in this case 8i. Then we have this variable r. And r is what's called the modulus of the expression. I'm not sure how much you've dealt with complex numbers in the complex plane, so I'm just going to do a quick little explanation of that. So the complex plane is very similar to the Cartesian plane we usually work in, right? Normally you'd have, x here and y here, and you'd have your 4 quadrants, right? But in this case, instead of x and y, we're going to have the real axis and the imaginary axis. And what this allows us to do is represent complex numbers in a graphical planar format. So in this case, our number is 8i, which essentially we're going to say 8i is really 0 plus 8i. And so when we put something on the complex plane, first we find the x coordinate, so to say, or the real coordinate, in this case 0, so it's going to be there. And then we go up the imaginary axis 8 units. And we'll just say that right there is 8. Now, just to clarify things, if this was, for example, 3 plus 4i, we would go over 3 and then up 4, and then that would be 3 plus 4i. Now, the reason we're doing this is because we need to find the modulus. And the modulus is going to be the distance from the origin of the complex plane to our expression. So for 3 plus 4i, for example, it's going to be this length right here. Luckily for us, we're not dealing with 3 plus 4i, we're dealing with 8i, which is actually just a line that's straight up and down. And since it's in the 8 position on the imaginary line, it's going to be 8 units tall. That's pretty sensible. So r in this case is going to be 8. If it was something like 3 plus 4i, well, then we would have to find the square root of 3 squared plus 4 squared, which is 5. So r for 3 plus 4i is 5. R for 8i is just going to be 8. Pretty fair. All right, now back to our formula we have. We know that r equals 8. All right, so now we have this letter n. And n is going to refer to the number of the root. In this case, 3. So 8 to the 1 over, whoops, 1 over 3. All right, now continuing down the line, cosine theta. Well, this is where we get into sort of the trigonometry of the situation. Theta obviously is referring to an angle, and what it's referring to is the angle from the real axis here to our line for 8i. And so if you go from here to here, that's going to be an angle of 90 degrees. So theta is going to be 90 degrees. Now if the line was, like we said, 3 plus 4i earlier, then that's going to be, 30 some odd degrees or something. In this case, we got it nice and easy, 90 degrees. So we don't have to do very much trigonometry, but since you're in trigonometry class, I'm sure you could find the angle if it was harder to find. For example, you would just make a little triangle here, and then knowing all 3 sides, you could do a lot of cosines and figure out the angles and whatnot. All right, 90 degrees plus 2k. Now this k is essentially going to be whatever iteration we're on. So if n equals 3, then k is always going to be starting at 0. It's a sequence of numbers that go all the way up to, actually let's make n something bigger for this instance. Let's make n 9. It's going to be continuing up all the way until you have n minus 1. In this case would be 8. Since n is 3, what that means is we're going to have k beginning at 0 like it always does. We're going to go up 1, 2. And these are the 3 values for k. The very convenient thing about complex roots is that the degree of your root is going to be the number of answers you have. So just like if you were trying to find the roots of something like an expression like this, you would say, oh, well, there's going to be 3 roots because 3 is the highest order. Well, in complex numbers, finding the nth root of complex numbers, it's always going to be the degree of your root is the number of answers. So cube roots will always have 3 answers. And each of these iterations of k is going to produce a different answer for us. So we'll start with 0, then we'll do 1, then we'll do 2. So we're going to do this formula 3 times, 1 for each value of k. All right, and so in this case we'll start with 0. Pi over n is 3 plus I, which we know is the square root of -1. We're just going to leave it as I, times the sine of 90 degrees plus 2 pi times 0 divided by 3. And then solving this formula is going to give us our first root, our first answer. And so let's do that real quick. 8 to the 1/3 power is 8 cubed, which is 2. We're going to have 2 times cosine of 0 times 2 times pi is 0. So 90 degrees plus 0 divided by 3 is 30 degrees. Plus I times the sine of the same thing over here, 30 degrees. These two are always going to be the same. So this is going to be our first root right here. So if we simplify that, cosine of 30 degrees, you look on your unit circle, you say, hey, that's root 3 over 2. And then plus I times sine of 30 degrees. Oh, you know, it's 1/2. And then we're going to distribute our 2 here to give us root 3 plus I. And that's going to be the first root of our expression 8i. We can check it just to make sure if we want. So if we multiply this times itself plus I, that's going to give us 3 times 2 root 6i plus -1. And if you do it again a bunch, it works. I'll tell you that much. We don't have to check it right now. So that's going to be our first root. Now we just do the same thing 2 more times, and I'll do it 1 more time, and then you can do the last one. So once again, our root z equals the modulus r, which in this case is 8, to the 1/3 times cosine of 90 degrees plus 2, and this is going to be, let me pull it up, oh, we're on the other side, 2k, and since we're on the next iteration, we're going to say k equals 1, 2 times 1 times pi divided by 3 plus I times sine of the same expression as the other one, 2 times 1 times pi over 3. And then we solve. Once again, this becomes 2 times cosine of pi is 180 degrees, so 2 times pi is 360 degrees plus 90, 450 degrees, divided by 3, 150 degrees, plus I sine of 150 degrees again. It's important to note, you can do degrees or you can do radians. Personally, degrees works better for me, but whichever way you feel. So then looking at our unit circle, 150 degree, cosine of 150 degrees is negative root 3 over 2 plus I times the sine of 150 degrees is going to be a positive 1/2, and then this is all multiplied by 2 to give us negative root 3 plus I. And that is the second of our 3 roots. And then the last root, I'll just tell you what it is. It's going to be negative 2i. and then we have root 3 plus I. So then these are our 3 roots using this fancy formula. Thank you to Mr. Abraham de Moivre who produced it. And one last time for posterity, I'll write it down nice and big somewhere on a piece of paper if I can find. Here we go. And then you can screenshot this or try to remember it. Z, which is our root, equals r to the 1 over n times cosine of theta, which is our angle in the complex plane, plus 2k, which is our iteration, pi over n plus I times the sine of theta plus 2k pi over n. And that right there is the ticket. So if you have that, that would be your best friend for finding any root of a complex number. You just remember that n is the degree of the root. So if you're finding the square root, that's going to be 2. The cube root is going to be 3. You know, the 20th root, that's going to be 20. And then k is just going to be the iteration starting at 0 and going up until 1 less than the degree of the root. So if I'm finding the 20th root, k is going to start at 0 and go all the way up at 19, and I'll have 20 different roots. The number of roots you have is equivalent to the degree of the root you're finding. And that's that. If you have any questions, you know where to find me.